This program is a presentation of UCTV for educational and non-commercial use only.
Each and every minute, we pay about $200,000 for imported petroleum. Energy production and use is implicated, as we've heard often in the last 2 days, implicated in greenhouse gas emissions and climate change. Energy production is also transforming landscapes. Many lease decisions that the Department of Interior puts forth are litigated. And I will suggest to you that these don't reside simply in oil and gas decisions, but also increasingly litigation on the establishment and investment in solar, in the Mojave Desert, wind, etc. So energy use, energy efficiency, energy conservation, thus, are universal concerns. The concern has moved beyond what it was perhaps in the 50s, 40s, 30s, beyond the realm of manufacturers seeking to reduce costs to the realm of policy, politics, and society as we seek to meet broad social, environmental, and economic goals. Now, energy usage, as we've heard the last 2 days, falls broadly into 3 categories. A third of the world's energy is consumed in buildings and the associated workplace and residential uses. Another third, approximately, is used in factories and plants, and a final third is used in transportation. Now, in each of those realms, some of them touched more on in these last 2 days than others, in each of them there are opportunities to do things differently. But before I address the political economy of where I think we're going and what is shaping that path forward, I want to reflect a little bit on where we are. I think this message merits repeating. Looking at the last 30 years, despite increases in total energy use, energy efficiencies of individual products are significant. We have not just started yesterday in the pursuit of energy efficiency. For example, today's refrigerators use about 1/3 less energy than electricity 30 years ago. From 1973 to 2001, the U.S. economy grew 125%, while energy use increased about 30%. Still a lot, but proportionate to the growth of the economy, there were some energy efficiencies along the way. During 1990s alone, manufacturing output climbed 41%, but industrial electricity consumption grew 11%. Clearly, pursuit of efficiencies enabled that to happen. Now, from the dawn of the industrial era to the present, we've seen, I believe, continuous efforts to do more with less, to dematerialize, to climb up the clean fuel ladder to conserve energy. We see technological wonders that use far fewer resources and less energy to do familiar tasks, and more looms on the horizon. We heard the presentation on nano production and nano structuring, which offers so much future potential. But think of a few common things that we now utilize. A single CD-ROM holds 90 million phone numbers, which replace at a telephone company 5 tons of phone books. Or consider fiber optics. 64 pounds of silica yields a communications network that carries 40 times the messages carried by a cable made from 1 ton of copper. Now, those innovations yield phenomenal savings in both resources and energy to get a job done. Or trucking. Think of the advent of GPS. We don't think of that necessarily as an energy efficiency innovation, and yet think of it with respect to a trucking company. A single trucking firm using GPS has been able to avoid 4 million miles of driving per year. Now, I call those innovations the Viridian Verge, Viridian being green, Verge being coming together, the coming together, if you will, the linking of economic action with environmental benefits. What is the bottom line of that brief technological tale? We've made conservation progress, but conservation is a journey, not a destination. There is no final endpoint. There is still much untapped potential at the intersection of energy, the economy, and the environment. And I believe those opportunities unfold along two dimensions. One dimension is technological innovations, but the other, a little bit discussed, but less discussed in these proceedings, is institutional innovations. Now, the role of technological innovation in adding value in the marketplace and in achieving energy efficiencies is well recognized. The past 2 days have been much about that, so I will scurry right past that subject, and instead let me focus on institutional innovation, an oft-neglected dimension of entrepreneurship, the economy, and environmental progress. For environmental entrepreneurship and energy efficiency entrepreneurship, I want to suggest that new institutional arrangements that improve environmental and energy performance fall into several categories, and let us explore a couple of them. First, those institutional arrangements and changes include new relationships between manufacturers and suppliers through green performance contracts. Now, I'm going to give you an example, not in the realm of energy efficiency, but I think you can see its application in energy as well. Let us consider Saturn. Saturn, the auto manufacturer, used to pay its paint supplier by the amount of paint it bought, by the volume of paint. But a while back, they switched to a contract in which they paid by number of cars painted. Now, think about that. That simple contracting change gave that supplier an incentive to think, oh boy, how can we make paint that really sticks well, is really efficient, and has no overspray? And so the effect of that was, in fact, new innovations in new paints that were extraordinarily efficient. Now, there are similar contracts between manufacturers and suppliers in the realm of energy efficiency that create incentives likewise. But let me move to the second category, and that is new relationships and interactions between producers and customers. And here, I do want to pause on something that has been discussed, and that is green building management. For example, situations in which energy managers or energy contractors fund investment in building owners, fund investment in energy-saving technologies. The buyer pays a portion of the energy savings over some fixed period of time to the contractor, after which the buyer then owns those efficiency assets. Now, this is not purely speculative. We've heard folks talk about it a little bit, but I want to talk about the Department of the Interior. Our Bureau of Land Management and our Park Service actually are engaged in that kind of contract. And by the way, a lot of folks said it couldn't be done because, remember, we have those 2,400 facilities. They're little. And none of those big energy contractors, Johnson Controls and blah, 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 technical term, none of those folks really wanted to tackle our small, dispersed locations. So what we did was to cluster our locations out there in the middle of Chaco Canyon, in the middle of nowhere in New Mexico, and we signed contracts with an energy efficiency provider that had a mobile van that went from place to place to place, did the analysis, and then we purchased across multiple facilities energy efficiency technologies, lighting, and so on and so forth. Now, we're seeing also, in a third category of institutional arrangement, emergence of new relationships among producers through waste exchanges or development of byproduct synergy contracts. Now, through those relationships, one company's waste becomes another's feedstock, or one company's waste becomes another's energy. I'm going to give you another example in the waste realm, but again, applicable for energy too. In Texas, a mini steel mill generated fly ash as waste, which in turn it sold to a Portland cement company as feedstock. Think of cogen plants. That's fundamentally what they're all about, producing one thing as waste in this company, utilizing it as energy in another. Now, those institutional and market contracting arrangements, I would argue, matter big time to the issues you've been talking about over the last 2 days, to the commercialization of product. Because they set the stage, they create the incentives. There was a lot of talk about, boy, let's have behavioral change and how do we make it happen? Well, you know, money is a great educator and a great behavioral changer. When you get those kinds of incentives aligned right, boy, people change what they buy. Now, those arrangements affect motivations of energy and materials users to seek out ever more efficient technologies and practices that reduce environmental impacts and enhance energy efficiency. Now, back to a point I made earlier, opportunities abound to better meet this nation's energy needs through conservation, lower impact technologies, through new management techniques. But I want to step away from that and think big, really big, and differently about the relationship to the world around us and its implications for energy efficiency. A few months ago, and some of you have heard me in different settings talk about this, a few months ago, the celebrated author Thomas Friedman dubbed 2008 as the year the Great Disruption began. Eyeing years of economic growth, eyeing disparities between rich and poor nations, eyeing so much consumption of stuff, Thomas Friedman opines that, and I quote, "We just can't do this anymore." He recycles a theme that recurs every so often for different reasons at different times since Malthus first warned of too many people consuming too much stuff. As other pundits judge the world's economy in terms of banking and credit and access to capital, Friedman talks of even bigger cataclysms of economy and the environment. We are, he says, simply running out of stuff, depleting the natural capital of the planet. Now, I think Friedman offers the wrong diagnosis for today's profound economic woes, but I want to get to the positive element of his message as well. I think he offers the wrong diagnosis for today's woes. He misses the dynamic processes in a competitive marketplace that enable us to do more with less, some of which have been discussed for 2 days. As far back as Henry Ford's first assembly lines, engineers measured and tinkered to reduce cost by reducing waste and energy use per unit of output. Even something as prosaic as the Coke can, and here it's late in the afternoon, so we're going to have some show and tell. Even something as prosaic as a Coke can has gone through multiple evolutions so that the once hard-to-crush metal can, I, of course, am way too young to remember the 60s, when it was a sign of virility to crush this can, but even today I can squash it, and if I'm lucky, I can rip it in two. Why is that? And what does it have to do with this conference? Why is that? That's because it now takes just 28 pounds of metal to make 1,000 cans, where 40 years ago, 1,000 cans required 168 pounds of metal. That is a process of dematerialization, new materials, etc., about which much of this conference is looking. Now, Friedman's diagnosis may be wrong, but he ends with a very important admonition, or perhaps it is a cheer. He cheers for economic assessment that sees opportunity in nurturing nature's capital. Now, natural landscapes, as described by scholar Gretchen Daly at Stanford, wetlands and sea marshes, watersheds of free-flowing rivers and streams, forests, grasslands, even urban parks and roadside tree canopy have multiple benefits for human communities. I am going to tie this to energy efficiency. These natural systems purify water, they moderate temperatures, they absorb pollutants from the air, they provide habitat for bees that pollinate crops, they protect coastal communities from storms, the list goes on and on. Yet the connection between these services and the natural world around us is often invisible and neglected. This neglect results in underinvestment in environmental protection and increased impacts from land, water, and coastal transformation. With ecosystem degradation come corresponding losses of natural system functions and their benefits to human communities. Now, why do I mention ecosystem functions in a conference on energy efficiency? It is because those losses of those natural functions do carry large and hidden energy costs. Natural systems provide for the most basic of human needs, services that enhance safety, health, and economic opportunity. Let me give you an example. The city of New York invested over $1.5 billion to protect and restore the Catskill Mountain watershed, a web of natural systems that for years, decades, had purified the city's water supply, but was undergoing degradation and development. They invested $1.5 billion to protect that watershed. Why? Because their alternative to meet safe drinking water standards was to invest $9 billion in mechanical filtration treatment plants. Now, investing in nature's capital saved the city money and enhanced habitat, a two-for a win-win, but it also translated into significant avoided energy use that mechanical water filtration systems would have required. Let me explore this theme a little bit more. American Forests evaluated that's a nonprofit organization, evaluated the extent of tree canopy in cities like Houston, Roanoke, Atlanta, etc. Houston lost 16% of its tree canopy over the last 3 decades, translating into a loss of annual air pollution removal services, if you will, pegged at about $38 million, and an annual loss of stormwater management services of about $237 million. Their alternative with that loss was to enlarge their stormwater treatment facilities and infrastructure. The loss also meant increased energy usage. Consider figures from one city, San Antonio. Lost tree canopy in San Antonio, so you guys are talking all of this high-tech stuff, really important. But some of our opportunities to achieve energy conservation, perhaps we call it, rather than efficiency, reside in nature services. In San Antonio, over a 15-year period, the loss of tree canopy is estimated to equate to about $17.7 million increase in residential summer energy costs. So all the while that folks are scrambling for new air conditioning devices and lighting devices and so forth, on the other hand, we're increasing our use of that stuff by chopping down all the trees in the city. Now, those examples highlight the significant services natural systems provide. Failure, I would suggest, to recognize those services results in decisions that diminish, degrade, and even destroy natural assets. The result of that destruction can be increased environmental harm, yes, higher costs to provide services such as water filtering, yes, and foregone benefits of energy savings and community safety. The 20th century was a time of paving over our cities. I believe the 21st century will be a time of recreating natural landscapes, natural urban streams, and other permeable landscapes, and that highlights the intersection, the criticality of converging biology and engineering. It highlights the relevance of materials innovation in infrastructure and buildings and energy systems. Now, buoyed by the expanding academic research on ecosystem services, some recent public policy is beginning to tiptoe in this direction and set the stage for our future. The Farm Bill of 2008, Record 2007, requires that the Department of Agriculture develop a framework for measuring those ecological services benefits, including, for example, energy savings from tree canopy, etc. EPA has actually now allowed watershed permits through which wastewater treatment plants may enter into trading arrangements with farmers to achieve permit requirements for temperature rather than installing high-cost and high-energy-consuming refrigeration systems, again, to achieve those temperature goals. One trade in the Tualatin River Basin resulted in payments to farmers of $6 million to plant shade trees in riparian areas, avoiding $60 million in costs to construct refrigeration systems and, of course, the ongoing operation costs of those systems. Now, let me make one thing clear. Investing in nature's capital offers economic opportunity, but it is also, I believe, a central foundation of 21st century environmentalism, and it is part of a smart energy strategy for this nation. Tree cover in urban areas east of the Mississippi has declined 30% over the last 20 years alone, while the urban footprint has increased 20%. Now, many here have explored technological opportunities for energy efficiency in lighting, computing, building design. I applaud those efforts. They're fantastic. They're fascinating. Some of you have examined energy sources beyond fossil fuels, alternatives that might be utilized. And this summit has explored crossing the bridge from innovation to implementation through economic investment and commercialization. But there is a political dimension to smart energy futures, a dimension shaped by context and challenges. And I want to mention a couple of those that take us perhaps seemingly far afield. I want to highlight three elements of a context that I think will affect energy politics and economics. This is the really big picture beyond direct energy policy about which you have heard something the last 2 days. And that first element, that first context, is water. Water. Moving water from where it is to where it is wanted is a major part of energy use in the West and elsewhere in the nation. That means there are huge opportunities to affect energy consumption that reside in rethinking water infrastructure and technology. And many energy sources require large amounts of water or can affect water quality. Energy production is linked to water. Let us think of that national ethanol goal. The 2012 target of 7.5 billion gallons per year of ethanol requires 30 billion gallons of water to process, equivalent to the total water needs of Minneapolis. If one quarter of the crop grown for ethanol needs irrigation, it would require nearly 1 trillion gallons of water per year. That's equivalent to the combined usage in all the cities of Arizona, Colorado, Idaho, and Nevada. Much energy production and use is linked to water, yet water constraints loom large. The National Science Foundation issued a recent report a year or so ago that concludes that abundant supplies of clean, fresh water can no longer be taken for granted. Not just in the West, where on Colorado's Capitol building is emblazoned the phrase, "Whiskey's for drinking, but water's for war," but rather across the nation. We've witnessed burgeoning populations in the nation's driest areas, 60% in Nevada, 40% in New Mexico, 30% in Colorado. Climate change is altering the availability and timing of water. Off-stream water withdrawals in the United States are estimated at 408,000 million gallons per day, or 3 times the average flow over Niagara Falls, enough water to fill the Astrodome every 2 minutes. Energy strategies, I would argue, thus, are linked to water strategies. They are intimately integrated and linked. Our energy efficiency futures, I believe, cannot ultimately help us go where we're going in isolation from contemplating water supply and water quality. Are there technologies to reduce energy requirements for supplying water to communities and farms? And as we supply energy, whether biofuels, fossil fuels, nuclear power, other fuels, how can we minimize water requirements? Now, this brings me to the second big context, and that is climate change. That's a no-brainer. It's a key driver of economics of energy. The politics of climate change will shape our energy futures. The advent of national climate policy will affect the relative costs of different energy options. But the devil is in the details. Therefore, the shape of energy futures will partly be linked to the shape of the climate policy future, and that is still a tale unwritten. The third contextual element is the relationship of land and energy supplies. Perhaps coming out of the Interior Department, this is near and dear to my heart. Many alternative energy sources, photovoltaics, wind, ethanol, and other biofuels, can be very land transforming. So, as we pursue clean energy and energy efficiency, I believe we need to broaden consideration of what we mean by what's green. Yes, the carbon footprint matters, but so too does the landscape footprint and wildlife impacts matter. We need only look right now at the Mojave Desert and the scramble to site solar and wind projects to anticipate challenges of land transformation. That scramble is already invoking lawsuits. By the way, at any point in time, the Interior Department is subject to 3,000 lawsuits. There's an old Chinese adage that observes that in our challenges reside opportunities. My challenge to those gathered is how do we minimize this broader environmental footprint of energy on landscapes, and that, in essence, introduces into the equation an additional design constraint. Our smart energy future also confronts other challenges. Some of those have been mentioned. Among those challenges is the marketplace itself and institutional procurement practices. We heard from the panel on consumer dynamics as well. My own research a decade ago on this topic affirmed the remark of the panelists, that is, that the willingness to pay more to buy green may indeed be limited. But procurement can create unnecessary impediments to technological adoption. Sometimes energy efficiency technologies and practices generate life cycle savings, but the costs are more upfront. Many firms and governments acquire goods calculating the relative upfront purchasing costs, but have no mechanism, no contracting mechanism, no acquisition mechanism to look at long-term or life cycle costs. Success, therefore, of energy efficiency technologies may hinge as much on changing contracting rules as on the merits of the technology alone. They will hinge, too, on procurement rules. I want to suggest one other thing, as folks talked about incentives and federal policies and state policies to encourage energy efficiency. I'd like to suggest that we do need to be wary of legislated technology prescriptions. Now, if there's prescribing your technology, you leap for joy. But that prescription, in fact, may preclude the advent of other new ideas. EPA currently has a potpourri of voluntary and mandatory energy efficiency standards for appliances, lighting, and other products, and also many certification programs. Regulations, standards, and certifications can stimulate results, and that is a good thing. But perhaps we need to emphasize performance standards rather than mandating specific technology outcomes. Now, I want to reference Yogi Berra, my favorite philosopher. He once opined that the future ain't what it used to be. Now, perhaps in a more sophisticated and less ironic way, scholar Richard White made a similar point when he wrote that, and I quote, "All the context in the world doesn't explain tomorrow, which is where you always end up." Now, I have offered some context. I have summarized some current circumstances, challenges, and trends, yet stuff happens. So I speak not as Cassandra peering into a crystal ball, but as a perennial optimist that human ingenuity will lead us to a better future. I think we saw that in the spectacularly innovative concepts presented over the last 2 days. But the intersection of the economy, politics, and energy is an agenda that transcends, I think you can see from my comments, energy itself. The politics and economics of energy demand, I think, holistic horizons. Those horizons include very fundamentally reconsidering water, how we deliver and use water, the relationship to energy sources, infrastructure, and uses. It includes a look at cityscapes, not just buildings, about which you have heard much in the last 2 days, but the landscapes in which buildings are situated. Self-evidently, it also includes transportation policy and politics, infrastructure, and conveyances. One speaker did suggest thinking of energy efficiency in the context of everything that uses energy as perhaps not helpful. I want to offer a different perspective on that question. For the political economy of energy, I believe we must look to its intersection with land, water, cityscapes, if you will, everythingism. As Peter Drucker, the noted management guru, once said, entrepreneurship opportunities lie anywhere and everywhere, so too do energy efficiency opportunities lie anywhere and everywhere, not simply in the traditional categories we think of. So perhaps as a political scientist, I want to suggest also as a final remark that there is an imperative to recognize the significance of political drivers to technological choices. Thank you very much.
But being the last speaker, there's sort of good news and bad news. The good news is whatever has to be said has already been said. And I just have 50 other slides to show you. But the bad news is you're stuck with me. So I'll try to be very brief. I just want to start off with a slightly different perspective. And the perspective is, before we get to sort of the details of technology, and I'm going to mostly talk about technology. That's my background. I'm not a policy guy, although I pretend sometimes to be. But I just want to show you this map. This is the population density in the world, all right? We are over there, right? This is LA, the dark spot. We are over here. I live in Northern California over there. And, you know, there's some spots in New York, Washington out here. The population densities in India and China, Japan, they're obvious, and Africa. And I want to then so this is the population density. This is roughly the energy usage in the world. And you can actually see the brightness out here. If the lights are a little off, we can actually see it better. And here's Europe, India, China, Japan, etc. What is interesting, and you saw this, I think Steve Denbar showed this before. What is interesting is if you overlay them together. And this is the overlay, which shows a mismatch. And the mismatch is that we had a few pockets of energy or population density, but look at this bright spot out here in the United States. And look at then the population densities, which are in red, and these people have not yet turned on their lights. And if they turn on the lights, metaphorically, in the way we have in the United States, we are toast. And so the big challenge is today, and while we should certainly talk with the United States, the big challenge is how do we turn off the lights in the right way without changing the lifestyle too much? We may have to do so, and economic growth. And how do we enable them to turn on the right lights, metaphorically? That's really the challenge of a lifestyle, of our lifetime, and many other lifetimes now. So this, I like this chart. This is CO2 emission per capita. You could put that graphic in many different ways. This is GDP per capita, so United States, high GDP, and also high CO2 per capita emissions. And this line out here is the average of the world. About roughly 5 tons of CO2 per person. So again, graphically now, the challenge is how do we bring United States down? There's no question we have a responsibility to do that. But the other part is, look at China and India and Brazil over here, all right, Mexico. All these are where the population growth is going to be. And at the end of the day, you have to, and people don't often like to say this, it is a population growth problem. Every indications around the world that the energy efficiency, energy per GDP, they're all in the right direction except for one vector, and that's population. And these people, and we have a double whammy out here. One is that these countries, the GDP per capita is increasing. And the second whammy is that population is also increasing. So we have a nonlinear effect out here. And the question that we have to ask is that will India, China, Brazil take this route, or will they take that route? And that route is extremely critical. Because if they take the US or the Western route, I think we are toast. In many ways, some of the things that we'll see around will be irreversible. And so we not only have to do this, but we have to enable the rest of the world to do that, this one out here. Because that is what it will take for us to survive, and you can call it sustainability and many different the words for it. But that's really where we have to be. Okay, so all that. Now let's concentrate on the United States. Okay, this is the energy supply and demand, which is very nicely put by Lawrence Livermore Lab. This is supply, and this is demand, and you can see these are put in numbers. And as an engineer, you like to put the numbers, data out there to see how much they are. And so this is petroleum, natural gas, coal, nuclear. This is the primary energy, nuclear. Solar, 0.006. And the thickness of these lines showing how much magnitude. And I don't think there's a font to show how small solar is today. So solar certainly has to be done, because that is, at the end of the day, the sustainable energy source. But to increase that at a rate that will make a dent in the primary energy supply We have to grow this industry at a really fast rate, and that requires some fundamental changes in our approach we do solar. And it was very nice to hear Ray Orbach talk about the actual fundamentals, the science that is required to really bring in game changes. Because that's what we need to accelerate this side, decarbonize that, and reduce the energy demand, and mix and match with the right supply and demand through transfer and distribution. Simply easier said than done, but that's what it is. All right? So, okay, so now what do we do? Well, I'll say a few words about Berkeley. This is on the supply side. We have a Helios project that was started about 3 or 4 years ago, and is essentially sunlight to fuel. And we said there are 4 primary routes, and we don't know which one's going to win. Okay? And we need to try out all 4, and we'll see 5 years from now, 10 years from now, which one is winning. Well, the 2 of them are biological. One is take the plant waste and turn that into hydrocarbon, not ethanol, but hydrocarbon, jet fuel or gasoline. How do we do that? And one is the waste, one is photosynthetic microbes, and turning that into hydrocarbons. And these 2 have been funded by, one by BP and the other by Joint Bioenergy Institute by Office of Science and DOE. And the 2 other ones are non-biological. And this is understanding photosynthesis at the fundamental level. We still don't quite understand how the photons are actually absorbed and they interact in some coherent way and split water and form, form carbohydrates at the end. We don't quite understand at the molecular level. And if we did, it's like learning flight from birds. Okay, we are at that stage. If you can just learn a little bit, we might be able to do better than photosynthesis. And that's the other approach. And finally, scalable PV, using materials that are abundant and that are cheap and that are non-toxic. And so that using photoelectrochemistry. So that's a Solar Energy Research Center for DOE. And this is on the supply side. There are other things going on. But I want to talk about efficiency. And this chart has been shown before, but we are proud to be in California. In fact, we are actually blessed to be in California. But how did this happen? This is per capita electricity consumption. This is year. And we are proud to have my division form at the turning point out here. This is often called the Rosenfeld effect, after Art Rosenfeld, because he was an inspiration for many of us, and he's still around. He's California, one of the commissioners. But there's both interplay between technology and policy working together. And the 2 policies that happened was the decoupling of the utilities. That is where the utilities are actually incentivized to sell less energy and actually make you more energy efficient and make money from that. And that, it's only been adopted in 10 or 11 states, and I mentioned that earlier. It should be a federal policy. And of course, the rate goes up a little bit, and but it's distributed. We all contribute to this. That's a sacrifice we all need to make. So anyway, so that's one. And the effect of that, I'll just show you one. This is the refrigerator. As someone mentioned refrigerators. This is a famous refrigerator chart. Energy use per unit of refrigerator. This is 1973 or so, peaked out there. And now it has been coming down. It's about 1/4 or 1/5 of the energy use per unit of refrigerator. And this is a combination of regulation and technology working together and bringing this down. And the price has actually come down in equivalent dollars. So it's not that it's more expensive. It's less expensive. It can get less expensive. And the size has actually increased. And that's limited by the size of your kitchen door now. Of course, people have refrigerators in the garage now also. But that's the size has increased. The impact of that is worth noting. Here is the impact, so now between supply and demand. Here is billion kilowatt hours per year. This is the energy use that would have happened by refrigerators in 1974 standards. And this is what it is today. And so that's the energy that it's saving per year. Compare that to 50 million 2-kilowatt PV system, Three Gorges Dam, okay, existing renewables without the hydro, and this is conventional hydro. So just by one appliance, you could do so much. And now think about all the appliances and the buildings, et cetera. And if one argues that we should, this is a great argument for saying that energy efficiency in appliances and buildings, et cetera, it'll pay for itself in the long run. Now let's talk about buildings. You've seen this chart before and seen these numbers. I'm going to go quickly. If we did nothing, by 2030, the buildings would need 16% more electricity, which means about 200 gigawatts of electricity capacity. And at whatever price we have, about $2 or $3 per watt, or sometimes $5 a watt, depending on the source, we're talking about $500 billion to $1 trillion investment, which means about $25 to $50 billion per year of capital investment in power plants if we did nothing, because the electricity demand increased. And so either we do that, and this is not even counting the carbon cost, or we make it more efficient. Which one is more, more cost-effective? I would argue that it is the efficiency, and buildings can provide grid-level storage. We're talking about grid and storage. Well, buildings can provide spinning reserves and storage. And both Michael McQuaid and I testified in front of Congress, myself in front of the Senate, and Michael in front of the House. And you can find these testimonies, and we sort of laid out what it needs, and it's actually very similar. So just to give you what the challenge is, so there is 2007 Energy Independence Security Act 2007, says zero net energy building. Wonderful. And if we did that today, I won't go into the details, if we reduce the energy by 80% in new construction and 50% in existing construction, if it happened today, we will not need the electricity from half the coal-fired power plants. That's the impact. And the energy that you actually need, if you provided that by nuclear, which is about 20% electricity, and other renewables, you would have a zero carbon footprint buildings and commercial buildings industry. And this is at a growth rate of about 1.7% per year. In China, it is 7%. In India, it's 8.5% growth. That's where the new buildings are really happening. And they are asking us for help in designing the right kind of buildings. And so this is the opportunity. The challenge is, let me show you what the challenge. And as an engineer, you have to look at this and say, wow. Here is the actual energy use intensity. That is the joules per square meter, or in this case, kilo BTU per square foot per year. Okay, it's still the same old units. And these are LEED buildings. This is data from LEED buildings, certified silver, gold, platinum. The average, that's the average. And the average, as you go to higher and higher rating, the average goes down. Well, and this average is lower than the national average, it's about 90. Right? But look at the spread in the data. Okay, this is all over the place. What is more interesting is if you plot the ratio of the actual measured performance, to the design performance, and plot it against the design intent, design performance. And so zero net energy is going this way. And what you find is that as you make the design tighter and tighter to zero net energy building, your actual performance goes about 2 to 3 times more. And so you defeat the purpose. This is actual data. We're not making it up. But if you loosen it a little bit, you actually can do better than the design performance. The point is, the design performance doesn't mean much at the end of the day, except to reduce the average. But for particular buildings, the actual performance could be way off, especially if you try to get to zero net energy. How did this happen? How come LEED is not using actual performance? Everything is based on simulation. Okay, simulation is great, but if you don't measure, you'll never know. And the problem is that the building codes today, we talk about, so California is very blessed, we got Title 24, but Title 24 is based on simulation, design performance, not based on measured performance. As an engineer, you say, hey, you got to measure things and find whether they meet some standards. We do that for a computer, we do that for a cell phone, we do that for everything. We see what is the performance for cars. So there is a mismatch out here. There's a lack of measurement and policies requiring it. And the fragmentation of the process will come to that later on. So that's a fundamental issue. And we are actually, now we're working with the peer program to see if they would actually support a study to see if you had measured performance, sort of beyond Title 24, Title 24 on steroids, if you may. What would be the economic impact? If you did better than a standard, could you trade your efficiency? Could you actually make money out of it if you are better than a particular standard? So that's a policy change with technology. So this is the fragmentation of the buildings industry. You have architects, structural, mechanical. It's a silo. They don't talk to each other. And then you have the actual process of designing. You have design, detailed design, working drawings, tender, planning, scheduling, and it's all sort of step-by-step process. And you put them together, you get all these operational islands which don't talk to each other. It's a major fragmentation. There is no system integrator, as opposed to the aerospace industry or the computer industry, where the system integrators, at the end of the day, Apple will give you a computer and will tell you this is how it will perform, and generally it performs that way. There's nothing like that in the building industry. And so we need to integrate the process communities, integrate the building system, align incentives. There's split incentives in this as well. So there's a policy, and one of the things that I have recommended is a policy innovation, just like decoupling. We need some kind of a decoupling for the buildings. That is national standards based on measured energy and indoor environmental quality performance. You cannot ignore the indoor environment, because you will then just shut off the lights, shut off AC, it'll be hot and sweaty, and you can save a lot of energy. But that's not what we want. So how do you balance that is very, very important. So anyway, this is the technical part we need. We don't have an operating system for a building. Just like we have for a computer, we don't have, how do you coordinate the activity and really make your building adapt to you or to the people? We don't quite have that. It is an open loop right now, essentially. And that operating system, the Unix for building, needs to be written, for which we have to understand how systems work, for which we need thermodynamics, fluid mechanics, heat transfer, controls. All the basics of engineering is required for this. We have some success story in New York Times building where LBL was asked to help in lighting, daylighting. This is daylighting next to windows, and this is electrical lighting. And we have worked with San Francisco Federal Building, which in San Francisco you should not need HVAC, or not AC at least. So this is naturally ventilated buildings, et cetera, which really reduces the cost. There's demand response, very important. This is a technology that was developed. We have a demand response research center, Marianne Piet leading it, supported by California Peer Program, where you have the utilities and their buildings. And here is using the internet for communication to say that if the demand goes up, can you turn off the thermostat, you change the thermostat, so that you essentially use the thermal inertia of a building, okay, as a storage medium, and so that it'll take you about 10 or 15 minutes to feel the difference, and by that time, you may have shaved off some peak load, and there's some real data where you can shave off the peak loads, et cetera. And this should be done, and this because the peak load is very, very expensive. Batteries, there was a talk on batteries which I missed, and Jean-Marie is, of course, a very well-known person in this area. A few of us happened to visit Tesla Motors, and we took a ride in the Roadster. If you get a chance, please do that, because then you'll realize this is 0 to 60 in 3.9 seconds. It's more acceleration than a plane taking off. And they ask you to turn on the radio, and you put your hand and they accelerate, and your hand goes back. And so power density is not the problem. It's the range of the car. The energy density is a critical problem. And the energy density is safety, lithium-ion, cycle life. Can you go to 1,000? Can you have a battery which lasts the car? Okay, several thousand cycle lives. And of course, cost is a major issue. The Tesla is very well positioned to be a powertrain company. And they will enable not only their own cars, they're coming out with a sedan at $50,000, which may be affordable to few, but they're enabling other smart cars and others. And I think electric cars, given the price differential between a kilowatt hour of gasoline or kilowatt hour electricity in China and India, will most likely see electric cars first happen in the Tata Nanos, which are much easier to retrofit than a Chevy Volt. And that we'll see probably happen. But nevertheless, this is something that battery in terms of energy density is absolutely critical, and we need materials knowledge. These are some limiting numbers out here. This is today's battery, which has doubled in capacity in the last 16 to 18 years. So this is the Moore's law for battery. Unfortunately, it's not very fast. But this is lithium-ion batteries with graphite anode, lithium cobaltate as the cathode. But there are other battery structures, and this is the standard 18650 cells. And the large batteries would go into the whole battery pack for Tesla is this big, and it's about 400 pounds, all made up of batteries like this into modules. And so the whole approach to batteries could potentially, needs to change, or how do you make batteries. But this is lithium air battery, lithium sulfide battery. This is 5,000 watt-hour per kilogram, and this is 300, on order of magnitude higher. But of course, there are fundamental issues to be solved. And this happens, I strongly believe, and I think many people believe, the fundamental understanding of materials at atomic and molecular scales, combined with nanostructured architecture, could lead to major advance in battery technology, and we really need to do that in the United States. Let me quickly, carbon capture sequestration. No, I don't think anyone's talked about this. But the United States, China, India, and Russia have the 4 biggest reserves of coal. And people will use that, all right? And because they need economic growth, there's no other, the renewables are not catching up fast enough. So we have to do this, carbon capture. Carbon capture is extremely expensive. Carbon sequestration is risky. So we have to address both these problems. So where is the cost? Well, let me show you. So today, how carbon capture, I'll just talk about the science behind it. So you have a CO2 absorber, then you absorb and you bind CO2 to something, then you regenerate it by heating. And then you post-process, pressurize it, and transport it and put it down. The carbon capture, the expensive part, is all out here, the capital and the operating cost. How is it done today? There are 2 fundamental chemistries for CO2. One is the photosynthetic chemistry, which is uphill. You need a photon, or you need few photons to go uphill. The other chemistry is downhill reaction, which is the bicarbonate reaction, all right? And all carbon capture today is there is no third chemistry, by the way. If someone can develop it, that would be fantastic. That'll be game-changing, potentially. So this is the bicarbonate reaction. You get carbon dioxide plus water, okay, and you get a bicarbonate. And then you react it with a base, a Lewis base, which is either an amine or a sodium or calcium ion. And you get calcium carbonate, sodium bicarbonate, and ammonium carbonate, et cetera. And these are different binding strengths and different affinities. And here's where the system-level performance and the chemistry plays a role. So the high binding strength, calcium carbonate, if you do high binding strength and high selectivity, you have a small size collector. Okay, so it's low capital cost because it's very efficient, it binds immediately. But then the operating cost is very high because you've got to break the bond somehow. So you've got to heat it at very high temperatures. So you got high-grade heat, and thereby you need to spend energy. And today, the carbon dioxide CO2 capture using amine capture or calcium carbonate capture is very expensive. 1/3 of the power from a coal-fired power plant goes into carbon capture, and that is too expensive. On the other hand, if you low binding strength, let's say amines, low binding strength, you can then use the waste heat of a power plant to decouple it because it's low binding. But on the other hand, you have high capital costs because you need a lot of it because the chances of it binding may be low. And so that's where the trade-offs are. However, if you can, the rate limiting step is this reaction. And if you can somehow enhance the rate with a catalyst, with some kind of a catalyst, then you could potentially get low capital cost and low operating cost. And that would be very interesting. By the way, we have catalyst enzymes in our body which does that all the time. It's called carbonic anhydrase. And that controls the pH in our blood, okay, as we speak. So can we emulate biology to have catalysts, maybe inorganic catalysts, with some zinc center, or with some metal center, to change this around? And if you could do that, it could potentially make a fundamental change in how we do carbon capture and reduce the cost. I cannot end a talk without a talk with thermoelectrics because that's what I do, and John and I have been collaborating for the last 10 years. I'll show you just, I think there was a talk by Lon Bell, wonderful talk on thermoelectrics. Let me just show a little bit. This is traditional thermoelectrics. It's a heat engine. It can be used for power generation, refrigeration, or heat pumping, and it's made of semiconductors. And today, the material, or the last 50 years, the material has been bismuth telluride. It's very expensive, and the efficiency is not high enough. And you have to increase a figure of merit called ZT. I won't go into the details of that. It is a combination of properties. And ZT needs to be higher than 2 at least, hopefully 3 or more, to be able to perform at a level that is cost effective, at like $1 per watt kind of thing. And this is the history of ZT from 1950s, and nothing much has changed except for the last few years. And this is one of the hardest problems in material science. How do you reduce a thermal conductivity material without reducing the electrical transport properties and actually enhancing it. I won't go into the details of this again, but this is a really hard challenge, and I know Ray Orbach has worked on this a long time ago in reducing thermal conductivities, et cetera. This is something that we have done jointly with Santa Barbara on using nanostructures to do what is called phonon scattering, and I won't again, but this is now potentially leading to ZTs which are higher than 1, maybe 1.5 or higher, and at higher temperatures as well. But I want to show something, and this is 3.5 material, something that we are quite excited about, but we don't know for sure if this is the right thing to do or not. But we are quite excited about this. And that is using silicon. And silicon is the most abundant semiconductor, and it is also, you got $100+ billion industry in manufacturing. And if that could be turned into thermoelectrics, that would be great. Except that bulk silicon is terrible. You got a ZT of 0.01, and that just doesn't cut it. And we serendipitously got into some nanostructuring of silicon, and where we found these are some nanowires which are roughened on the surface. And that roughness, surprisingly, and we're still verifying it in many different ways, reduces the thermal conductivity to a point that makes the ZT about 1. And that there's some fundamental physics that potentially could come out of it. Again, I won't go into the details. But this, if we verify it over the next year or so, this could potentially change the game, because if you can raise the ZT beyond 1 in these materials, low-cost materials, this could be quite interesting. Let me stop here by putting the chart again of the overlay. And I think this is sort of the global picture. And let me stop here, and I think I've taken more time than I should have. I appreciate your patience and your attention. Thank you very much.